Good afternoon, everyone. So, in the last class, we have looked into several problems in parabolic partial differential equations, whatever can be solved using separation of variable, and we took up relevant chemical engineering problems, namely the transient heat conduction problem in one dimension, and we looked into the basic problem, what is classified as the basic problem, which is a well post problem. Then we talked about the ill post problem, where the initial condition is homogeneous, but the boundary conditions are not, one of them is homogeneous, another is non homogeneous. Then we have looked into the basic problem, where the initial condition is non homogeneous, but the boundary conditions are homogeneous. Then we looked into the method of how to convert the ill post problem into well post problem, and finally, we took up some of the real life chemical engineering heat conduction problem, and so we solved them using separation of variable. Now, there are two kinds of boundary conditions in the actual problem we have looked into. One is the boundary conditions at Dirichlet boundary condition. In the next problem, we completely solved the problem, and the next problem is the boundary condition is Neumann boundary condition. The problem we are solving and we could not finish in the last class, where the one of the boundary condition is non homogeneous, and it will be the Robin mixed boundary condition. So, that means whatever the heat that has been arrived at that boundary by conduction is taken away by convection. So, we were solving that problem in between. So, let me complete that problem first, then we will move into multidimensional basic problem, parabolic in nature, which can be solved by using separation of variable. So, let me look into an actual chemical engineering problem, heat conduction problem, but one dimensional, transient heat conduction problem, but one dimensional. So, the governing equation is the energy balance equation. So, if we write down the energy balance equation, rho Cp del T is equal to K del square T del x square. So, del T is nothing but alpha del square T del x square, where alpha is known as the thermal diffusivity. That will be having a value expression K by rho Cp. So, now we fix up the general boundary conditions. At T is equal to 0, temperature of the problem was temperature of the in the plate, it was T naught, and at for this is valid for every x. For at x is equal to 0, the temperature was kept constant and maintained at a temperature T 1, that is valid for every t, and at x is equal to L, T is equal to minus K del T del x is equal to H T minus T infinity, where this term left hand side represents minus K del T del x is equal to the energy that has come at that boundary located at x equal to L by conduction, and that amount of energy has been taken away by the ambient, by the convection present in the ambience. So, H is the heat transfer coefficient and T infinity is the ambient temperature. Now, let us look into how many non homogeneities are there in this particular problem. There are three sources of non homogeneity. One is in the initial condition, another is the boundary condition, and because of the presence of this temperature T infinity in the boundary condition located at x is equal to L. So, there are three sources of non homogeneity in this problem. So, we make this problem non dimensional, so that the number of sources of non homogeneity will be reduced, and at least by defining an appropriate temperature, non dimensional appropriate temperature, we can reduce the number of non homogeneities from 3 to 2. Now, let us look into that. At by define a non dimensional temperature theta as T minus T infinity divided by T 0 minus T 1 T0 minus T infinity. Let us define it that way, and at it does not matter whether you write T0 minus T infinity or T1 minus T infinity, but the idea is this has to be equal to 0 at one of the boundaries. So, let us define theta like this, and of course, x star is x upon L, where L is the length in the of the plate in the x direction. So, if you put this all these things in the non-dimensional form, so your basic equation will be T0 minus T infinity del theta del t is nothing but alpha T0 minus T infinity del square theta divided by L square del x star square. So, T0 minus T infinity will be cancelled out. So, you can write del theta del tau is equal to del square theta del x star square, where tau is non-dimensional temperature and it is T alpha over L square. That is the non-dimensional tau. Let us look into the boundary condition and initial condition at t is equal to 0. That means, at tau is equal to 0, this is equivalent to tau is equal to 0. Theta was t is equal to t naught. So, you just put t naught minus t infinity divided by t naught minus t infinity. So, theta is equal to 1. At x is equal to x star is equal to 0, t is equal to t 1. So, therefore, theta is equal to t 1 minus t infinity divided by t 0 minus t infinity. This is a non-dimensional temperature and it is constant. So, let us put this value as theta 1, and at x is equal to x star is equal to 1, we have minus k t 0 minus t infinity del theta del x star. So, there has to be an L here is equal to h t minus t infinity, we write t 0 minus t infinity times theta. So, you can these will be cancelled out and you can bring it to the other side. So, del theta del x star plus b I theta is equal to 0. That is a mixed boundary condition at x star equal to 0, where b I is nothing but the Biot number and this is equal to h L over k. So, let us look into the problem. We made this governing equation non-dimensional and made the independent variable x star well behaved between 0 and 1. At the same time, we had the initial condition theta is equal to 1, which was not equal to 0. This is non-homogeneous initial condition. The 1 this term represents the non-homogeneity. Theta is equal to theta 1 at x star is equal to 0. That is also a non-homogeneous term, but on the other hand, the boundary condition at x star is equal to 1 has become homogeneous. So, in this way, we have by this way of defining the theta, we have reduced the number of non-homogeneities from 3 to 2. So, we define this problem into 2 sub problems considering one non-homogeneity at a time. So, theta is equal to theta 1 plus theta 2. Let us define theta 1. Theta 1 will be del theta 1 del tau is equal to del square theta 1 del x square. We just write x in terms in place of x star. So, that means x is a non-dimensional length. At tau is equal to 0, we put theta 1 is equal to 1. At x star is equal to 0, we put theta 1. Okay. Since there is a clash in nomenclature, we call this as theta 1 superscript naught. So, at theta is equal to at x star is equal to 1, theta 1 is equal to theta 1 naught. At x star is equal to 1. So, we force it to this boundary condition, we force it to 0. So, we consider only one non-homogeneity at a time. So, x star equal to 1, we have del theta 1 del x star plus b I theta 1 is equal to 0. That is the definition of theta 1. Let us define theta 2. Theta 2 is governing equation is del theta 2 del tau is equal to del square theta 1 del x square. At tau is equal to 0, theta 2 is equal to 0, at x star is equal to 0, theta 2 is equal to theta 1 superscript, and at x star is equal to 1, we have del theta 2 del x star plus b I theta 2 is equal to 0. So, therefore, we have divided this problem into two sub problem considering one non-homogeneity at a time. We kept the non-homogeneity in the initial condition as it is in the problem number theta 1. In problem theta 2, we and in theta 1 we kept the non-homogeneity at time t equal to 0, but we forced the non-homogeneity present at x star equal to 0 to 0. So, we just forced it to vanish. On the other hand, in case of theta 2, the initial condition was taken as homogeneous, but we kept the non-homogeneous term in the boundary condition as it is. So, we divide this problem into two sub problems, so that we consider one non-homogeneity at a time. Now, if you look into the problem of theta 1 is a well posed problem, because it has a non-homogeneous initial condition and homogeneous boundary condition. So, this is definitely a well posed problem, and if we look into the problem number theta 2 second sub problem, in the second sub problem the initial condition is homogeneous, but one of the boundary condition is not homogeneous, it is inhomogeneous, the other one is homogeneous. So, therefore, this is an ill posed problem. We have already seen the solution of this kind of well posed problem earlier, and if you remember, the solution is something like this. So, the eigenvalues for this problem are obtained by the roots of the transcendental equation alpha n tan alpha n plus Bayet equal to 0. Roots of these transcendental equations are given by the are the eigenvalues of this particular problem, and sign functions are the eigenfunctions. So, the complete solution of this problem is theta 1 is equal to summation of C n e to the power minus alpha n square tau sin alpha n x. Okay. So, where C n is obtained by carrying out this integral sin square alpha n x dx from 0 to 1, and in the numerator it is integral f x is 1 in this case. So, it will be integral of sin alpha n x dx from 0 to 1. So, this gives the complete solution of theta 1, and we can we know what is the solution of this. We have already proved this solution earlier. So, if we want, we can look into the solution of C n once again. So, C n first we evaluate the denominator. The denominator is 0 to 1 sin square alpha n x dx. So, it will be half 0 to 1 2 sin square alpha n x. So, this will be nothing but cosine 1 minus cos 2 theta is equal to 1 minus 2 sin square theta. So, 2 sin cosine 1 minus cosine theta or 1 minus cosine 2 alpha n x dx. So, the first part is half minus half, this will be integral of cosine 2 alpha n x dx 0 to 1. So, this will be half 1 minus sin 2 alpha n x divided by 2 alpha from 0 to 1. So, this will be half 1 minus sin 2 alpha n, we put x is equal to 1 minus sin 0 is 0. So, divided by 2 alpha n, and we expressed sin 2 alpha n in terms of cosine 2 alpha tan alpha n. So, this becomes 2 alpha n tan 2 tan alpha n divided by 1 plus tan square alpha n, and if we look into the transcendental equation must satisfy tan alpha n is equal to minus Biot bi divided by alpha n. So, we are going to put it there. 1 minus 2 alpha n is 2, tan alpha n is minus minus plus bi alpha n square divided by 1 plus bi square divided by alpha n square. So, this, so half 1 plus bi alpha n square plus bi square. So, this becomes half alpha n square plus bi square, and on the numerator you have alpha n square plus bi plus bi square. So, that is that goes the denominator, and if we look into the numerator becomes integral 0 to 1 sin alpha n x dx. So, integration of this will be giving you minus cos alpha n x divided by alpha n 0 to 1. So, it will be 1 minus cosine alpha n divided by alpha n. So, we get the complete solution of theta 1. So, theta 1 will be summation n is equal to 1 to infinity C n is given by this equation of C n is first we find out C n is numerator divided by denominator. So, it will be 2 1 minus cosine alpha n divided by alpha n, and your denominator is alpha n square plus beta I square divided by alpha n square plus beta I square. So, that is the coefficient C n. So, now you are in a position to write down theta 1 completely, summation n is equal to 1 to infinity. We put the value of C n 1 minus cosine alpha n divided by alpha n multiplied by alpha n square plus beta I square divided by alpha n square plus beta I bi plus bi square Biot square e to the power minus alpha n square tau sin alpha n x. So, that gives the complete solution for the problem theta 1. Now, let us look into the problem theta 2. Now, if you look into the problem theta 2 is an ill-posed problem, and we just look into the solution of theta 2. So, we make the problem ill-posed problem, we convert the ill-posed problem to well-posed problem. Now, if you do that, what you will be getting is that we, since the time dependent part, the initial condition is having is homogeneous, we break down the problem into two sub problem. One is theta 2 s, that is a function of that is a steady state solution, it is a function of x alone. Another is the unsteady state solution transient problem, that is a function of x and tau both. So, therefore, we put this equation into the governing equation. If we put this equation in the governing equation, for this then we will be collect the similar terms, and we will be getting the governing equation of theta 2 s and theta 2 t. So, this becomes del theta 2 t del tau is equal to d square theta 2 s d x square plus del square theta 2 t del x square. So, we define theta 2 s and we define theta 2 t. Now, if you look into the definition of theta 2 s, it will be simply d square theta 2 s d x square is equal to 0, subject to the boundary condition that at x star is equal to 0, we have theta 2 is equal to theta 1 0. So, theta 2 s plus theta 2 tau is equal to 0 is equal to theta 1 0. So, we associate this non-homogeneous term with the steady state solution to force the theta 2 t, the boundary condition theta 2 t to be homogeneous. That means, we put the boundary condition at x star as theta 2 s is equal to theta 1 0. Now, let us put the boundary governing equation of theta 2 t. Del theta 2 t del tau should be is equal to del square theta 2 t del x square. Now, at x star is equal to 0, since we have associated the non-homogeneous part with the steady state solution, then theta 2 tau will be must be equal to theta 2 t must be equal to 0. That simply makes the corresponding boundary condition of the transient solution to be homogeneous. Now, let us look into the other boundary condition, that is at x star is equal to 1, we have del theta 2 del x plus Biot theta 2 is equal to 0, put theta 2 is equal to theta 2 s plus theta 2 t, and then separate the collect the similar order terms. So, we will be getting the boundary condition at of theta 2 s at x star is equal to 1, that will be del theta 2 s del x plus b I theta 2 s is equal to, so it becomes d theta 2 s dx, this becomes total derivative. So, this is the boundary condition on x star equal to 1, and this is the boundary condition on x star is equal to 0, and the boundary condition at x star is equal to 1 for, so x star and x they are basically same. For theta 2 will be del theta 2 t del x plus b I theta 2 t is equal to 0. Now, look into the initial condition at tau is equal to 0, your theta 2 was equal to 0, therefore, theta 2 t will be nothing but minus of theta 2 s, which is a sole function of x, and in fact, that is the solution of the transient, that is the solution of the steady state part. Now, if you look into this problem, now this and this theta solution of the steady state part will be known by solving, you will be getting this. So, if let us talk about the steady state solution, then we will come back to the transient problem. So, d square theta 2 s dx square must be equal to 0. So, this has a solution theta 2 s is nothing but c 1 x plus c 2. Now, at x star is equal to 0, at x is equal to 0, theta 2 s is equal to theta 1 0. So, therefore, theta 1 0 is nothing but c 2. So, therefore, theta 2 s is equal to c 1 x plus theta 1 0. Now, we use the other boundary conditions at x star is equal to 1 d theta 2 s dx, d theta 2 s dx is nothing but c 1 plus b I theta 2 s evaluated at x star is equal to 1. So, this is equal to c 1 plus theta 1 0 is equal to 0. So, therefore, c 1 can be written as minus Biot theta 1 0 divided by 1 plus Biot number. So, you will be having the solution of steady state part is nothing but minus b I theta 1 0 divided by 1 plus b I times x plus c 2 is nothing but theta 1 0. So, we have a solution theta 1 0 is equal to 1 minus b I x divided by 1 plus b I. So, that is the profile of the solution of theta 2 s as a function theta 2 s, that is the steady state solution as a function of x. This profile I am going to put it over here. So, theta 2 t or the transient part is nothing but theta 1 0 multiplied by 1 minus Biot times x divided by 1 plus b I. So, if you look into this problem, the problem has the non-zero initial condition with a known function here and homogeneous boundary condition at x is equal to 0 and homogeneous boundary condition at x is equal to 1. So, this is a well posed problem and we know how to solve this problem. We have seen it at least 2 times earlier. So, again we use the separation of variable type of solution, since this is the the mixed boundary condition is the boundary condition at x is equal to 1. We will be having a transcendental equation, roots of which will be denoted by the eigenvalues will be obtained from the zeros or roots of that equation, and eigenfunctions will be sine function, and by using the initial condition we can finally evaluate the unknown coefficient of integration, and finally we can obtain the solution of theta to t. Since we have already solved this problem earlier, I am not solving this problem here again. So, it will be a repetition only. So, we can get the complete solution of theta to t. We have already got the complete solution of theta to s, then and we have already obtained the solution of theta 1. So, the overall theta profile as a function of x and tau can be obtained as theta 1 x and tau plus theta 2 s, which is a function of x, and theta 2 t, which is a function of both x and tau. So, we got the complete overall solution of this particular problem, which is an actual heat conduction problem in chemical engineering application. Okay. So, that covers more or less the parabolic 2-dimensional parabolic partial differential equation, 1 dimension in space, 1 dimension in time, and we have looked into the problem with all sorts of non-homogeneities present in the initial condition as well as in the boundary conditions, and what will be the effect of different boundaries and how different boundaries can be handled by breaking down the problem into sub problems considering one non-homogeneity at a time. Now, we have also looked into the actual problem in chemical engineering system, where all the initial and boundary conditions are non-homogeneous. We have reduced the number of non-homogeneities by defining an appropriate non-dimensional quantity, so that the number of non-homogeneities is reduced at least by 1 from 3 to 2, and then we divided this problem into sub problems considering one non-homogeneity at a time and solved them completely. For the if the problem becomes a 0 initial condition and homogeneous initial condition and non-homogeneous boundary condition, then we divided the problem again into 2 sub problems considering one non-homogeneity, considering the problem is a linear combination of time independent part, that is a steady state part, and time dependent part, that is the transient part, and then we formulated we defined the corresponding problems of the steady state part and the transient part, and we solved them completely. Now, so that gives a wide coverage of different types of parabolic equations in 2 dimension one can encounter with. Now, we will be looking into higher dimensional parabolic partial differential equations. Now, we will be looking into this problem for higher order of when the function, when the temperature may be a function of x and y. So, actually if you look into the problem, it becomes if you remember what is called lumped system analysis. In the lumped system analysis, we have assumed it is again a heat conduction problem. If you remember what a lumped system analysis in heat transfer, then things becomes clear whenever we will be having a multidimensional problem, or wherever we will be having only a single dimensional problem in time only. So, what is lumped system analysis? In lumped system analysis, if Biot number is less than 0.1, that means if what is Biot number? H L over K of thermal conductivity of solid is less than 0.1. H is the heat transfer coefficient, L is the characteristic length, K s is the thermal conductivity of solid. If that is less than 0.1, then the variation of temperature in space within the control volume can be neglected. So, that means conductivity is so high corresponding to the convective heat transfer coefficient, then this is less than 0.1 means this thermal conductivity of solid is at least one order of magnitude higher compared to the heat transfer coefficient, convective heat transfer coefficient. That simply means, since the conductivity of the solid is pretty high, the temperature at different parts of the solid becomes almost instantaneously uniform. Now, that simply indicates that there is no temperature gradient exist within the solid. That means, temperature is not a function of space. That means, temperature is not a function of x, y, z coordinate system. Temperature is almost instantaneously equal throughout the whole mass of the solid. Therefore, in this case, the whole control the solid mass can be treated as a lumped mass, and it will be the temperature will be function of time alone, and you will be landing up an ordinary differential equation as governing equation of heat balance. Of energy balance of the system. On the other hand, if Bi is not less than 0.1, in that case the thermal conductivity is not that high compared to convective heat transfer coefficient. So, there exists a temperature gradient within the solid itself. That means, temperature profile in the solid is a function of space. In that case, temperature will be function of x in one dimensional problem, temperature is function of x and y in two dimensional problem, temperature function of x, y and z in a three dimensional problem, and temperature variation is most important. And since it is now it is varying as a function of x, y, z, original x and y, it becomes no longer a one dimensional problem, it becomes a two dimensional problem or multidimensional problem, whatever the case may be. If it becomes a multidimensional problem, a problem involving more than one dimension, that means it involves more than one independent variable. Therefore, we are going to land up into a partial differential equation instead of an ordinary differential equation in case of lumped system analysis. So, in this case, if Biot number is not less than 0.1, then temperature is a function of time as well as space. In general, it is a function of x, y, z, and the governing equation, and we will be landing up with a partial differential equation as governing equation of energy balance. Okay. So, in this, so let us look into that. So we are in the earlier examples, we have considered it is a function of temperature, a function of time and space alone. So, we landed up with two ordinary different two independent variables, and therefore, we are landing up with a partial differential equation involving two dimension, one in time, another in space x. If we talk about temperature function of x, y and t, we will be landing up with a three dimensional problem. If we consider that temperature function of x, y, z and t, we will be talking about a four dimensional problem, three dimensional in space and one dimension in time. So, these are the higher dimensional parabolic partial differential equations. So, let us look into a well behaved problem or a basic problem in three dimension, that is one dimension in time and two dimension in space. Okay. So, a basic parabolic problem. So, the governing equation of this problem will be rho C p del T del T. Okay. So, typical governing equation, we will be talking about the chemical engineering application later on. So, typical governing equation will be del U del T is equal to del square U del x square plus del square U del y square. So, therefore, we need to specify one initial condition on time, two boundary conditions on x, and two boundary conditions on y, because it is order 2 with respect to x as well as with respect to y. Now, let us to consider a basic problem, that means the initial condition is non-homogeneous and all the 4 boundary conditions are homogeneous. Let us see what we get. That is a basic problem in 3 dimension. At t is equal to 0, we have u is equal to u naught, and at x is equal to 0, we have u is equal to 0, at x is equal to 1, we have u is equal to 0, at x is equal to, at y is equal to 0, we have u is equal to 0, at y is equal to 1, we have u equal to 0. That means, all the 4 boundary conditions are homogeneous and they are Dirichlet boundary condition. Dirichlet and homogeneous boundary conditions. So, we talk about a basic problem where the initial condition is non-zero and the 4 boundary conditions are homogeneous. Now, since this operator is a linear operator, we again we can use the separation of variable type of method. We assume that solution of u is composed of 3 parts. It is a multiplication or product of 3 quantities. One is function of time alone, another is a function of x alone, another is a function of y alone. That is the case, then we consider that u is equal to function of time x, which is a function of x only, capital Y, which is a function of small y only. So, if that is the case, we put this equation in the governing equation del u del t. So, this becomes x times y dt dt is equal to del square u del x square, that means t into y d square x dx square plus t into x d square y dy square. We divide the problem, we divide both sides by x, y and t. So, we get 1 over t dt dt is equal to 1 over x d square x dx square plus 1 over y d square y dy square. So, the left hand side is a function of time alone, the right hand side is a function of space alone. So, therefore, they are equal and they will be equal to some constant. We call these constants as minus lambda square, and this constant cannot be 0 or positive. If this is 0, they will be giving a trivial solution. So, we will be getting, so let us again consider this part 1 over x d square x dx square is equal to minus lambda square minus 1 over y d square y dy square. Now, the left hand side is a function of x alone, the right hand side is a function of y alone, and they are constant and they will be equal, and they are equal and they will be equal to some constant. Let us consider this constant is, let us say so there will be some constant. Again, this constant can be 0, positive or negative. We have already seen if this constant is 0 and positive, we will be getting a trivial solution. So, this constant is negative. So, this will be minus alpha square. Okay. If this is the case, then we will let us look into the x varying part 1 over x d square x dx square is equal to minus alpha square. So, we will be getting d square x dx square plus alpha square x is equal to 0. So, this is again a standard eigenvalue problem or a Sturm-Liouville problem, and let us fix up the boundary conditions of this standard eigenvalue problem. So, d square x dx square plus alpha square x is equal to 0. Now, let us put the boundary conditions. and the boundary condition of the original problem must be satisfied by the x varying part. Boundary conditions on x must be satisfied by the x varying part. So, at x is equal to 0 in the original problem, your u was equal to 0. So, therefore, x, y, t is equal to 0, y and t we cannot comment on this, they will be not equal to 0. So, therefore, x is equal to 0 at capital X must be equal to 0 at x is equal to 0. Similarly, at x is equal to 1, u was equal to 0. So, therefore, capital X is equal to 0. Now, if you remember, this is a standard eigenvalue problem and these are the homogeneous Dirichlet boundary conditions. So, this we know the solution of this problem. The solution of this problem is that we have the solution as alpha n is equal to n pi, where index n runs from 1, 2, 3 up to infinity. So, alpha n are eigenvalues and eigenfunctions are x n c 1 sin n pi x. So, we completely solve the x varying part. Let us look into the y varying part. If you look into the y varying part, it becomes 1 minus lambda square minus 1 over y d square y dy square is equal to minus alpha square. So, we put it on the other side. So, 1 over y d square y dy square should be is equal to minus lambda square plus alpha square. So, this is a constant, and again this constant has to be a negative constant, otherwise this is a combination of two constant and this constant has to be a negative constant, otherwise you will be landing up with a trivial solution. So, this must be equal to minus beta square. So, therefore, we will be getting the governing equation of y as d square y dy square plus beta square y must be equal to 0. So, you obtain the governing equation of y varying part. So, if we look into that, d square y, we get d square y dy square plus beta square y is equal to 0, where beta square minus beta square is nothing but minus lambda square plus alpha square, or lambda square is nothing but alpha square plus beta square. Now, let us look into the boundary condition of the y varying part. If in the original problem at y is equal to 0 and y is equal to 1, we had u equal to 0, that means y must be equal to 0 on the both boundaries. Now, again this is a standard eigenvalue problem, as this is a special form of Sturm-Liouville problem and the boundary conditions are homogeneous boundary conditions. Again we know the solution of this. The solution is beta m is equal to m pi, where the index m runs from 1, 2, 3 up to infinity. So, these are the eigenvalues. And the corresponding eigenfunctions are y m, nothing, that will be nothing but C 2 sin m pi y. So, why we have put an independent index here m, because this is an independent eigenvalue problem. So, therefore, on the other hand, the x varying part was also independent eigenvalue problem with the index n, and this will be an independent eigenvalue problem with index m. So, therefore, lambda we can write it as lambda m n. So, lambda m n square is nothing but alpha n square plus beta m square. So, alpha n is equal to nothing but n square pi square and beta m square is m square pi square. So, therefore, we can write it as n square m square pi square. So, this gives the complete specification of lambda m n. So, we have already almost solved the problem, only the time varying part has to be found out. If you look into the time varying part, it will be 1 over t dt dt is equal to minus lambda mn square. So, we write it correspondingly, we write it Tmn as a subscript to correspond that it will be corresponding to particular lambda mn value. So, this will be giving a solution Tmn is nothing but another constant C3 exponential minus lambda mn square t. So, we construct the corresponding solution in Umn, that will be Tmn multiplied by the xn multiplied by the ym. So, therefore, Tmn will be C1, C2, C3, it will be new constant, let us say Cmn sin n pi x sin m pi y exponential minus lambda mn square t, where where lambda mn square is nothing but m square plus n square pi square, and we can construct the complete solution u as a double summation of u m n 1 over index m is equal to 1 to infinity, this is from index n equal to 1 to infinity. So, this will be double integral n is equal to m is equal to 1 to infinity, n is equal to 1 to infinity C m n sin n pi x sin m pi y e to the power minus lambda m n square t. So, we have got almost the complete solution. So, what is left is we have to evaluate the constant C m n. For that, we have to use the initial condition that has been unutilized till now. So, we have already utilized two boundary conditions in x, we have already utilized two boundary conditions on y. So, one initial condition at t is equal to 0 is unutilized, we use that is at t is equal to 0, u was equal to u naught. So, we put it that u naught is equal to double summation, one is over m, another is over n C m n sin n pi x sin m pi y. Now, what do we do? We multiply both side by sin m pi x and sin n pi y dx dy and integrate over the domain of x and y and utilize the property of the property that the eigenfunctions are orthogonal functions. So, multiply both sides by sin m pi x sin n pi y dx dy and integrate over x and y. If you do that, since u0 is a known function, so it will be u0 is constant. So, u0 is taken out, integral x is equal to 0 to 1, y is equal to 0 to 1 sin m pi x sin n pi y is equal to summation double integral C m n sin n pi x sin m pi x sin m pi y sin n pi y dx dy. Now, if we open up this summation series, this integral one is over x, another is over y. So, if we open up this integral, all the terms will vanish because of the orthogonal property of the eigenfunctions sine function. Only the terms where m is equal to n, they will be remaining and they will survive. So, it will be 0 to 1. So, only one term will survive, that will be sin square n pi x dx and 0 to 1 sin square m pi y dy. So, the answer of this is half, this will be half. So, you will be getting 1/4. So, there will be a Cmn here. Okay. So, we can 1/4 times Cmn. So, we will be getting Cmn as four times u naught integral 0 to 1 sin m pi x dx 0 to 1 sin n pi y dy. So, this becomes 4 u naught, it will be minus cosine m pi divided by m pi x divided by 0 to 1 multiplied by minus cosine n pi x n pi y divided by n pi evaluated from 0 to 1. So, this will be 4 u naught 1 minus cos 0 is 1. So, it will be 1 minus cosine m pi divided by m pi, and it will be 1 minus cosine n pi divided by n pi. So, ultimately you will be getting 4 u naught 1 minus cos m pi into 1 minus cos n pi divided by m n pi square. So, we will be in a position to get the complete solution u as a function of x and time is equal to 4 u naught double summation, one summation is over m 1 to infinity, another summation is over n 1 to infinity, 1 minus cosine m pi 1 minus cosine n pi m n pi square sin n pi x sin m pi y e to the power minus lambda m n square times t, where lambda m n square is nothing but m square plus n square into pi square. So, this gives the complete solution in 3-dimensional problem. So, this gives a complete solution in a 3-dimensional problem where all the boundary conditions are Dirichlet boundary condition. Next, we will be talking about some of the conditions are may be Robin mixed, or some condition may be a Neumann boundary condition. Then what will be the form of this solution, and then we will take up couple of standard chemical engineering problem to solve by using separation of variable. Once we do that, next we will move over to a 4-dimensional problem, that is the most general problem in chemical engineering application. It is 1-dimensional in time and 3-dimensional in space. So, we stop here, we will take up this we will solve those problems whatever I just mentioned in the next class. Thank you very much.